welcome back to my class in linear algebra. For today, we will take up another way for obtaining the inverse of a square matrix. Last time, we took the inverse of a square matrix using elementary row operations. For today, we will find the inverse of a square matrix if the inverse exists by using adjoint of a matrix and using determinant. First, we write the sort of formula for getting the inverse of a matrix using adjoint and determinant. If A is a square matrix of order n, this means that only a square matrix can have an inverse if it has an inverse. And matrix A should be a square matrix of order n. If a matrix has order n, that means the square matrix A has n rows and n columns. And not all square matrices have inverse. And you will see the reason why in this formula. The inverse of a matrix is denoted by A to the power minus 1 and is equal to the reciprocal of the determinant of A multiplied by the adjoint matrix of A. The determinant of a square matrix is a single numerical value associated with a square matrix. That means that only square matrices have determinant. We can only associate a determinant to a square matrix. Matrices that are not square matrices have no determinants. And the adjoint of a matrix A is the transpose of a matrix whose entries are the cofactors of the entries of matrix A. And the adjoint of matrix A is multiplied by the reciprocal of the determinant of square matrix A. And this is the reason why not all matrices have inverse. Because if the determinant of A is equal to 0, then the reciprocal of the determinant of A, if the determinant of A is 0, will not exist. Because 1 over 0 is not defined. Therefore, if the determinant of a square matrix is 0, you can surely conclude, you can confidently conclude that the given matrix has no inverse. First, we take how to find the adjoint of a square matrix. We consider the following square matrix. We let the entries of matrix A be denoted by A sub ij because A is a matrix of order n. The subscript j goes from 1 to n, and also the subscript j, which gives the column number of the entry A sub ij, goes from 1 to n. Then the cofactor of the ij entry of A is the ij entry of A sub ij. And the cofactor of the ij entry of A, denoted by C sub ij, is given by this formula. C sub ij is the cofactor of the ij entry of matrix A and is equal to negative 1 to the power I plus j, where I is the row number of the entry A sub ij, and j is the column number of the entry A sub ij. Negative 1, quantity negative 1 to the power I plus j multiplied by m of A sub ij. M of A sub ij is called the minor of A sub ij. Again, M of A sub ij is called the minor of the entry A sub ij of matrix A. And the minor of this entry A sub ij of matrix A, denoted by M of A sub ij, is defined as the determinant of the entries, the remaining entries, after deleting the ith row and the j column of matrix A. We now take an example for 2 by 2 matrix. For our first example, consider the following problem. Find the inverse of a 2 by 2 matrix with entries in the first row, negative 1, 3, entries in the second row, 5, 2, using adjoint and determinant. We start by getting the determinant of matrix A. If the determinant of matrix A is equal to 0, you stop and you conclude that the inverse of A does not exist. If the determinant of A is non-zero, then you proceed to get the adjoint of matrix A and then the inverse of matrix A. And this is how we evaluate a 2 by 2 matrix to get its determinant in general. In general, if the square matrix A has entries A, B, C, D, then the determinant of matrix A denoted by this absolute value notation, but it's not actually an absolute value of A. This notation represents the determinant of matrix A. And the determinant of 2 by 2 matrix is obtained by sort of using cross multiplication. You multiply D by A, we get AD minus, it's always minus, multiply C by B or BC. D multiplied by A is the same as A multiplied by D because multiplication of real numbers is commutative. And this is always minus, the sign between these two terms is always minus. The product of C multiplied by D, which is equal to B multiplied by C because multiplication of real numbers is commutative. So we proceed to find the determinant of A, the given matrix A, and if it's equal to 0, you stop and you conclude the given matrix A has no inverse. We find the determinant of the given matrix A, multiply 2 by negative 1, or negative 1 multiplied by 2, minus, always minus, 5 multiplied by 3, or 3 multiplied by 5. And we get negative 1 multiplied by positive 2 is negative 2. Minus 3 multiplied by 5 is minus 15. And minus 2 minus 15 equals negative 17. The determinant of matrix A is negative 17. And negative 17 is not equal to 0. Thus, the given matrix A has an inverse. And we proceed to get the adjoint of matrix A. And the adjoint of matrix A is the transpose of the matrix whose entries are the cofactors of the entries of matrix A. And we get the cofactor of each of this entry of matrix A. Beginning with this entry, negative 1, this is the entry in the first row and first column, and we denote its cofactor by C sub 1, 1. C sub 1, 1 is equal to, by the formula I wrote earlier, is equal to quantity negative 1 raised to 1 plus 1. Multiplied by the minor of negative 1. And negative 1 raised to 1 plus 1 is negative 1 raised to 2, and negative 1 square is positive 1. Multiplied by the minor of negative 1. The minor of negative 1 is the determinant of the remaining entries of matrix A after deleting the first row and the first column. If you delete the first row and first column of matrix A, the remaining entry is 2, and we get its determinant. The determinant of this is not an absolute value. The determinant of a single entry matrix is equal to that entry. So determinant of 2 is 2 multiplied by 1 is 2. Next we get the adjoint of matrix A is equal to the transpose of the matrix whose entries are the cofactors of matrix A. The cofactors of the entries of matrix A. And the cofactor of minus 1 is 2. Next, we get the cofactor of 3. 3 is the entry in the first row and second column. So the cofactor of 3 is denoted by C sub 1, 2. And the cofactor of 3, or C sub 1, 2 is equal to quantity negative 1 raised to 1 plus 2. Multiplied by the minor of 3. And negative 1 raised to 1 plus 2 is equal to negative 1 raised to 3. And negative 1 raised to 3 is equal to negative 1. Multiplied by the determinant of the remaining entries of matrix A by deleting the first row and second column of A. And the entry that remains is 5, and its determinant is denoted by And the determinant of a matrix with single entry is equal to the entry. So this is negative 1. Determinant of 5 is 5 multiplied by negative 1 is negative 5. And we write here the cofactor of 3, negative 5. Next, we find the cofactor of 5. 5 is the entry in the second row and first column. Hence, we denote its cofactor by C sub 2, 1. And the cofactor C sub 2, 1 is quantity negative 1 raised to 2 plus 1. Multiply by the minor of 5. Negative 1 raised to 2 plus 1 is the same as negative 1 raised to 3, and negative 1 raised to 3 equals negative 1. Multiply by the minor of 5, which is the determinant of the entries that remain after deleting the second row and first column of matrix A. Delete the second row and first column of matrix A, and the entry that remains is 3, and we get its determinant. The determinant of a single matrix, of a matrix with single entry, is equal to that entry itself. Hence, the determinant of 3 is 3 multiplied by negative 1 is negative 3. And we write this in the transpose of this matrix. Cofactor of 5 is negative 3. Lastly, we find the cofactor of 2. 2 is the entry in the second row and second column. We denote its cofactor by C sub 2, 2. And the cofactor C sub 2, 2 is equal to quantity negative 1 raised to 2 plus 2 multiplied by the minor of 2. Negative 1 raised to 2 plus 2 equals negative 1 raised to 4, and negative 1 raised to 4 is positive 1. Multiplied by the minor of 2, which is the determinant that remains after deleting the second row and second column, and the entry that remains is negative 1. Again, this is not the absolute value of negative 1, but the determinant of negative 1, and again, the determinant of a matrix with single entry or a 1 by 1 matrix is equal to that entry. Hence, the determinant of negative 1 is negative 1. Multiplied by 1 is negative 1. And we write the last entry of this matrix, whose transpose we should get to find the adjoint of matrix A. And the transpose of a matrix, as we have taken in the previous lessons, is obtained by writing the rows of the matrix as columns of the transpose of the matrix. For the transpose of this matrix, we write the first row as the first column of the transpose. So the entries in the first column will be 2, negative 5. And we write the entries of the second row as the entries in the second column of the transpose. And the entries in the second column will be negative 3, negative 1. And finally, we divide the adjoint of matrix A by the determinant of matrix A, or we multiply the adjoint of matrix A by the reciprocal of the determinant of matrix A. And earlier we get the determinant of matrix A equals negative 17, and its reciprocal is negative 1 over 17. Thus, the inverse of matrix A is equal to the reciprocal of the determinant of A The determinant of A is negative 17 and its reciprocal is negative 1 over 17 multiplied by the adjoint of matrix A, which is 2, negative 3, negative 5, negative 1. And this is matrix scalar multiplication of a scalar by a matrix. To multiply a matrix by a scalar is to multiply each entry of the matrix by the scalar. We multiply negative 1 over 17 by 2, we get negative 2 over 17. Negative 1 over 17 multiplied by negative 3 is positive 3 over 17. Negative 1 over 17 multiplied by negative 5 is positive 5 over 17. Negative 1 over 17 multiplied by negative 1 is positive 1 over 17. And this is now the inverse of A. Now we check if that is correct by multiplying A by the inverse of A, denoted by A to the minus 1. This is matrix A and this is A to the minus 1. And if we get the correct inverse of matrix A, the product of these two matrices should be the identity matrix of size 2 by 2. We multiply the first row of matrix A by each entry of the matrix A to the minus 1. We have negative 1 multiplied by negative 2 over 17 is positive 2 over 17, plus 3 multiplied by 5 over 17, that's 15 over 17, plus 2 over 17 is 17 over 17 or 1. Next, we find the entry here in the first row, second column. By multiplying the first row of matrix A by the second column of the matrix A to the minus 1. We have negative 1 multiplied by positive 3 over 17 is negative 3 over 17, plus 3 multiplied by 1 over 17 is positive 3 over 17. Therefore, we have negative 3 over 17 plus 3 over 17 is 0. Next, we find the entries of the second row. The entry here in the second row and first column is obtained by multiplying the second row of matrix A by the first column of A to the minus 1. We have 5 times negative 2 over 17 is negative 10 over 17, plus 2 multiplied by 5 over 17 is 10 over 17. Thus, we have negative 10 over 17 plus 10 over 17 is 0. And the entry here is obtained by multiplying the second row of matrix A by the second column of matrix A to the minus 1. We have 5 multiplied by 3 over 17 plus 2 multiplied by 1 over 17 equals 15 over 17 plus 2 over 17, that's 17 over 17 or 1. And this is the identity matrix of order 2 or size 2 by 2 or shape 2 by 2. Thus, we have shown that the product of A and the matrix A to the minus 1 is the identity matrix of order 2. Therefore, this matrix A to the minus 1 with these entries is the inverse of A. For your practice, please try the following exercises. Find B to the minus 1, that's the inverse of matrix B, if it exists using adjoint of B. Check your answer. In number 1, the matrix B is a 2 by 2 matrix with entries negative 4, 5, 2, 7. In number 2, B is also a 2 by 2 matrix with entries 6, negative 3, negative 4, 0. In each of the following numbers, you get first the determinant of matrix B. And if the determinant of matrix B is not equal to 0, you proceed to find the adjoint of matrix B. And finally, the inverse of matrix B. If you get a 0 for the determinant of matrix B, you stop and you conclude that matrix B has no inverse. And that completes our lesson for today for finding the inverse of a matrix using adjoint of a matrix and determinant of a matrix. And we will continue this lesson in the next video, tutorial video, by finding the inverse of 3 by 3 matrices. 3 by 3 is square matrices. Thank you for joining me in my class today in linear algebra.